You're listening to Würth Elektronik's What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our own Würth Elektronik technical specialists who are going to shine a light on our topics like energy harvesting, wireless power, AMI, and so much more. Make sure you tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik What's Up podcast. Next generation battery chargers used in industrial appliance applications such as power tools often require isolated AC to DC power supplies with high efficiency, low profile, low standby power, and small form factor along with multiple outputs. The UCC 28711 Flyback power supply controller provides isolated outputs without the use of an optical coupler. This translates into fewer number of components on the board. This controller processes information from the auxiliary flyback winding for precise control of output voltage and current. Quasi-resonant mode with valley switching reduces switching losses. The primary side MOSFET turns on during the first valley at maximum load. The UCC 28711 has a maximum switching frequency of 100 kHz and always maintains control of the primary peak current in the transformer. Texas Instruments reference design PMP 21927 takes a universal AC voltage input and creates three isolated 15-volt outputs. The main output can be loaded up to 1 amp and achieves over 86% efficiency. The other two isolated 15-volt outputs can be loaded to 50 milliamps each. Using primary side regulation usually gives plus or minus 5% regulation accuracy related to the output voltage, and normally it's avoided when multiple outputs are involved. In this design, the low current outputs have LDO linear regulators to keep the voltages within 1% regardless of cross-loading conditions. The transformer is a principal component in these designs. Building a transformer is often a repetitive process with many incremental changes that can affect the overall efficiency. In today's podcast, we bring you a webinar from Swaroop Vaidayanath, product definition engineer and the creator of the application note which this is based. Swaroop focuses on the flyback transformer design with multi-isolated outputs used in PMP 21927 and discusses the many design considerations taken to achieve high efficiency while maintaining a low-profile part for power tool applications.
Hello world. My name is Swaroop Vaidayanath, product definition engineer, transformer specialist at Würth Electronics. I have been in this role close to 9.5 years now, and I take care of custom transformer requests from major semiconductor companies in US for their power supply designs ranging from less than 1 watt up to 500 watts. So today's topic is about a 15-watt multi-output flyback transformer design. I co-wrote this app note with John DeRosa from Texas Instruments. Unfortunately, he couldn't join us today. So we will be discussing the design considerations taken to achieve over 86% efficiency for industrial appliance applications. So here is the agenda for today. We'll be briefly visiting about the PMP 21927 Texas Instruments design, and then go over the flyback transformer parameters. We'll be getting a little mathy and calculate duty cycle, turns ratios, current sense resistor calculation, primary and secondary peak currents, primary inductance, primary and secondary RMS currents, and selection of the core and the bobbin. We'll go over the construction and the transformer wire sizes, estimate losses. We'll look into testing and efficiency graphs, and finally conclusion. So Texas Instruments reference design PMP 21927 takes a universal VAC input and creates three isolated 15-volt outputs. So the main output can be loaded up to 1 amp and achieves over 86% efficiency. The other two isolated 15-volt outputs can be loaded to about 50 milliamps each. Using primary side regulation usually gives plus or minus 5% regulation accuracy related to the output voltage, and normally it is avoided when the multiple outputs are involved. But in this design, the low current outputs have LDO, linear regulators, to keep the voltages within 1% regardless of cross-loading conditions. So the transformer is a principal component in such designs, and building a transformer is often an iterative process with many incremental changes that can affect the overall efficiency. So in this webinar, we will focus on the flyback transformer design with multi-output isolated outputs and discuss the various design considerations that have been taken to achieve high efficiency while maintaining a low profile for power tool type of applications. So here are the transformer design parameters. So we have an input voltage range of 85 to 265 VAC, output of 15 volts at 1 amp, output 2 and output 3 at 15 volts at 50 milliamps. That's after regulation. We have an auxiliary winding, 18 volts at 20 milliamps. Frequency is about 70 to 80 kilohertz. And for this design, we will be meeting UL 60950 with reinforced insulation. And this transformer runs in DCM mode. So the maximum available duty cycle is determined based on DCM, resonant time TR, the target switching frequency at max load, Fmax, and the demagnetizing duty cycle, Dmax CC. So the demagnetizing duty cycle is the secondary diode conduction duty cycle during the constant current operation. So it is internally set by the TI chip UCC 2871X family at 0.425. And all the equations that have been listed below in the next few slides are referenced from the TI's UCC 2871X controller family datasheet. So the Dmax is 1 minus TR by 2 times Fmax minus Dmax CC. So that gives us 0.495. Next, we'll look into the primary to secondary turns ratio. And since we have three outputs, we will use the output with the highest power of 15 volts at 1 amp, as that's a good starting point. And the maximum primary to secondary turns ratio, NPS1, is calculated at the maximum frequency at full load, along with the estimated DCM resonant time. And the minimum input capacitor bulk voltage, that's V bulk min, the regulated output voltage, VOCV, the secondary rectifier forward voltage drop at near zero current, which is VF, and the target cable compensation voltage at the output terminals, that's VOCBC. So this is the equation. NPS max is Dmax times V bulk min by the Dmax CC times VOCV plus VF plus VOCBC. So substituting all these values, we get 6.3, and we will round this down to 6. So that's the primary to secondary turns ratio for this design. We'll now look into the secondary windings turns ratio. So the turns ratio of the additional secondary windings is based on the regulated secondary, and that can be calculated using the V out S2 plus VF by V out S1 plus VF. So that gives us 1.11. And since the turns ratio for the secondary 3 is the same as secondary 2, so with the actual turns, so we just round that up to the next full turn. With now we'll look into the auxiliary windings to secondary windings turns. So the bias supply from the auxiliary winding is used for voltage sensing and powering the IC. Hence, the winding is kept on the same side of the bobbin as the primary winding. The aux winding also operates at the same time as the secondary windings. So this turns ratio NAS1 is calculated using the bias supply under voltage lockout, the UVLO voltage, which is 7.35 volts. And again, this is a device parameter. The auxiliary rectifying diode forward voltage drop of 0.7 volts, the minimum desired output voltage during constant current mode, which is VOCC at 6.09 volts, and the forward voltage drop of output rectifying diode at 0.5 volts. There is additional energy supplied to VDD from the transformer leakage inductance, which allows a lower turns ratio to be used in many designs. So substituting all these values, we get 1.22 as the aux winding to secondary windings turns ratio. Next, we calculate the current sense resistor. So the transformer turns ratio and UCC 2871X, constant current regulating voltage, determine the current sense resistor for a target current of 1.3 amps. As not all of the energy stored in the transformer is transferred to the secondary, the efficiency term is included. And at the design phase, we can assume 3.5% of leakage inductance, about 5% of core and winding losses, and 1.5% of bias losses, for an overall transformer efficiency at 90%. So the RCS, current sense resistor, can be calculated as VCCR times NPS1 times square root of eta by 2 times IOCC. So that gives us a value of 0.75 ohms. Next is the primary and secondary peak currents. So peak currents are important in calculating the required primary inductance needed in the transformer. And the primary peak current is simply the max current sense threshold at the controller divided by the current sense resistor. So that is VCST max by RCS gives us 1.0307 amps. The secondary peak current is the primary peak current times the turns ratio NPS1 of the transformer. So ISP max is IPP max times NPS1, which gives us 6.184 amps. The peak current of secondary 2 can be calculated using these equations. The LS2 is LP by NPS2 square, which is 450 microhenry by 5.4 square. That gives us about 15.43 microhenry. And the NPS2 is NPS1 divided by NS2S1, which is 6 by 1.11 gives 5.4. And the power at O2 is the same as P at O3, which is 16.7 volts, the output, times 50 milliamps, which is 0.835 watts. So the I peak S2 is given by square root of 2 times PO2 by F max times LS2, which gives us 1.16 amps. So here comes the primary inductance calculation. I know I did mention the primary inductance on the previous slide, but I wanted to keep both the primary and the secondary peak currents on the same slide. So I just moved the primary inductance on the next slide. So the primary inductance of the transformer LP is calculated using the standard energy storage equation. E is equal to half Li square. So the parameters required are the primary peak current, max switching frequency, total power, and the transformer efficiency. So P out, total power, is calculated as 7.03 watts. And using this now, substituting all the values, we get the primary inductance to be 445.9 microhenry. So we can round this to 450 microhenry, considering plus or minus 10% of tolerance. So now we'll look into the RMS currents calculation. The primary and secondary RMS currents are important to find the right wire sizes in the transformer. So the primary RMS current, IRMS pri, is dependent on the peak current, IPP, and the maximum duty cycle, Dmax. So that gives us the IRMS pri to be 0.42 amps. The equation for secondary RMS current is dependent on the secondary peak current and the demagnetizing duty cycle. So substituting the values, we get 2.33 amps. So the RMS currents on the secondary 2 and the secondary 3 windings can be calculated using these couple equations, which is IDC is I peak times D by 2, and IRMS is I peak square root of D by 3. So the IS2 and IS3 are the maximum output DC currents, and D of S2 is the estimated duty cycle of the off time for the secondary 2 and 3 windings. So that comes up to be 8.62%. So now that we know the peak current and duty cycle, we can calculate the total RMS current for the second and third windings, and then divide it by 2 to get the individual RMS currents. So IRMS sec 2 is I peak S2 times square root of D offset of S2 by 3, which gives us 0.20 amps. So now we have to pick the core and the bobbin. So for power applications below 500 kilohertz, manganese zinc material is preferred as it performs well, and it has a permeability of 2000 to 2500. The TP4A core material is used in this design, and its saturation flux density is 390 millitesla at 100 degrees Celsius. So calculating the total input power, Pin, this is just P out by the efficiency, which is 18.92 watts. So now we will use this below equation that has been derived from switching power supplies A to Z by Sanjaya Maniktala. So this equation gives us the effective volume of the core. So core volume V in centimeter cube is 31.4 times Pn times mu by Z into frequency, max frequency times B sat square times R into 2 by R plus 1 square. So the relative permeability mu R is set to 2000 and the max flux density is set to 300 millitesla. And one of the most important considerations in flyback transformer design is not to saturate the transformer. So the core air gap Z, the AL no gap by AL gap is set to 10, and the current ripple ratio R, which is the peak current, the ripple current delta I to I is set to 0.4. So using all these, substituting all these numbers, we get 2.37 centimeter cube. So from the custom capabilities catalog by Würth Elektronik, the core volume of an EFD25 package is 3.3 centimeter cube, and the core volume of an EFD20 is 1.46 centimeter cube. Hence, we'll choose EFD25 through hole package as it meets the core volume criteria and the other requirements, such as a low profile height, an extended rail to meet the safety standards and the reinforced insulation, and also the 12 pins that are needed for this multi-output design. So now we can look into the wire sizes and construction. So based on thermal considerations, we choose the current density J to be 10 amps per millimeter square, as mentioned in the book Optimal Design of Switching Power Supply by Zanio, Shah et al. The wire sizes are selected as below. So the primary wire is RMS primary by this current density term J, which is 0.42 by 10 amps per millimeter square, which gives us 0.042 millimeter square, and the equivalent is 0.23 millimeter diameter. For the secondary windings, it is again the IRMS secondary divided by the current density. So that gives us 2.33 by 10 amps per millimeter square, which is 0.233 millimeter square, which is an equivalent diameter of 0.54 millimeter. So we need to choose the wire diameter to be less than twice the skin effect depth for proper utilization of copper. So the skin depth at 100 degrees in millimeters can be calculated as 76 by square root of the frequency, the max frequency. So 76 by square root of 80,000 gives 0.269 millimeters. So the wire diameter should be less than twice the skin depth, or 0.538 millimeter. So it's basically twice that 0.269. So taking all these parameters into consideration, a 28 gauge wire is chosen for primary and aux windings, and a 23.5 gauge is chosen for the secondary windings. And whenever wire sizes needs to be picked, thicker wire is preferred, as it provides lower resistance. And for low current secondaries, the 2-3 38 gauge wire is used. So yeah, this figure shows the construction of the transformer, the various layers. So since there are more turns on the primary side, the primary is split to get better coupling and decrease the overall leakage inductance. So half the primary winding is wound first, followed by the 15 volt 1 amp secondary winding, and both the 16.7 volt 50 milliamp secondary windings. The aux winding is wound next, and finally the other half primary. So there are layers of tape separating each winding, and triple insulated wire is used on the 3 secondary windings, and the standard magnet wire is used on the primary and aux windings. So this is done for 2 reasons. First is to keep the cost low, as the triple insulated wire is more expensive than magnet wire, and there are fewer turns on the secondary windings. The second reason is to reduce the overall fill rate. So the creepage and clearance distances are met as defined in the UL 60950 for reinforced insulation. So we meet about a working voltage of 265 VRMS and over voltage category 2 and the pollution degree 2 environment. Yeah, next week we'll look into the losses. So the core loss can be estimated using this figure. Since this application uses a unipolar waveform and the above chart is applicable to bipolar waveforms with Dmax as peak to peak, we must divide the magnetic flux density by half to use this chart. So we previously chose a max magnetic flux density of 300 millitesla. So dividing this by half gives us 150 millitesla. So using the 100 kilohertz curve from the above chart, so if we at 150 millitesla, there is an approximate core loss per volume of about 150 milliwatt per centimeter cube. So when I say milliwatt per centimeter cube, it's the same as kilowatt per meter cube, scaled say 10 times 10 to the power of minus 6. So multiplying this value with the core volume of the EFD25 package, which is 3.306 centimeter cube, gives us the approximate core loss. So in this case, it is 496 milliwatts. So the simple, now looking into the copper losses, the copper loss is estimated using the I square R loss. So the RMS currents were already calculated previously. So the copper loss gives us 381 milliwatts. So the total transformer loss is core plus copper loss, which gives 877 milliwatts. And the efficiency can be calculated as 1 minus the 877 milliwatts divided by the power, which gives us 94.85% theoretical transformer efficiency. So to calculate the theoretical temp price, a simple and fast estimate of temp price can be made by looking up the RTH of the core, which represents the temperature rise for 1 watt of losses. So for EFD25 core, the RTH is 30 Kelvin per watt. So multiplying the total losses gives us the temp price above ambient. So in this case, it is 30 times 0.877, about 26.3 degrees Celsius. So now we look into the testing and the efficiency graphs. The overall board efficiency was measured by loading the main 15 volt output. The other two 15 volt outputs were loaded to 50 milliamps and kept in regulation using LDOs. So the data is on the left side, and we just plotted an efficiency graph for the 120 VACI input. We do the same exercise with a 230 VAC input. Going with a 90% transformer efficiency during the design phase for calculations for this 3-output flyback transformer is a very good estimate. The AC losses and bobbin fill factor should be taken into consideration as well. And as mentioned, building a flyback transformer is an iterative process, but these guidelines should lessen the number of iterations to get an optimum solution in about 2 revisions. So on a system level, this 15-watt multi-output offline flyback design achieved over 86% efficiency, taking switching losses and other component losses into consideration.
To view the materials, download the application note, and replay the webinar on demand, click the link attached in this podcast. You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists who will shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Würth Elektronik What's Up podcast.